Welcome to Programming Fluency. This is Section 12.1, Project Specification. For 11 chapters, you learned C one piece at a time. Now you will build one real program from start to finish. But great programs start with a plan, not with code. In this video, you will learn to read a specification and turn it into a plan. Let's begin. You have spent 11 chapters learning C, one concept at a time. Now it is time to put it all together into one real program. But before you write a single line of code, you need to know exactly what that program must do. This is the plan for this video. First, what a specification is. It is a contract that says what the program must do, not how to do it. Next, the wordfreq spec. We spell out its inputs, its outputs, and its error cases. Then edge cases. These are the boundaries where bugs like to hide. After that, turning requirements into data structures. A struct, a growable array, and the access patterns. Finally, pseudocode and a checklist, so you can verify the plan before you write any C. This is the big change. Until now, every exercise told you exactly what to write. Real software is not like that. Someone hands you a description of what the program should do. Nobody tells you which struct to use or which function to write. You read the requirements, find the inputs and outputs, spot the edge cases, and plan the design yourself. That description of what the program should do is called a specification. Learning to read one is the core skill of software development. So what exactly is a specification? It defines what a program must do without saying how to do it. Think of it as a contract between the person who needs the software and the person who builds it. A good specification answers 3 questions. First, what goes in? Those are the inputs. Second, what comes out? Those are the outputs. Third, what can go wrong? Those are the error cases. Now the definition. A specification is a precise description of a program's required behavior. It covers inputs, outputs, constraints, and error handling, but it does not tell you how to build it. The spec is the what. Your code is the how. This is the project. It is a command line tool called wordfreq. Its purpose is to read a text file, count how often each word appears, ignoring case, and print the top N words, most frequent first. You run it by typing /wordfreq, then the file name, and optionally -n an account. Look at the arguments. The file name is required and it has no default. The -n count flag is optional and it defaults to 10. So if you leave off -n, the program shows the top 10 words. Now what counts as a word and what does the output look like? A word is a maximal run of alphabetic letters. A to Z punctuation, digits, and whitespace are all separators. The comparison is case insensitive, though with a capital T and the in lowercase count as the same word. Words are stored in lowercase. This is real output from running wordfreq on Moby Dick with -n5. Each line is a count, then a space, then the word, sorted by count, largest first. And when 2 words have the same count, they break the tie in alphabetical order. That exact output format is part of the contract too. Let's start analyzing. The first step in requirements analysis is to list exactly what the program receives. Do not think about code yet. Just list what comes in. Wordfreq has 2 kinds of input. First, command line inputs. That is the file name which is required and the optional -n count flag. Second, file inputs. That is the actual contents of the text file, which is lines of words separated by non-letter characters. Every one of these needs to be checked. A missing file name, a file that does not exist, a negative count. All of them are inputs the program must handle without crashing. This careful listing has a name. It is called requirements analysis. You do it before you write any code, and the result is a clear understanding of what the program must do. Now list what the program produces. There are two separate streams, and keeping them apart really matters. First, the normal output. That goes to standard out. It is one line per word in the format count then word, sorted by count, with ties broken alphabetically, and at most in lines. Second, the error output. That goes to standard error. It includes the usage message when there are no arguments, a error message when the file will not open, and a message for a bad dash and value. Why keep them separate? Because a user might redirect standard out into a file. If your error messages went there too, they would end up buried inside that results file. Sending them to standard error means they still show on the terminal. Now the part where bugs love to hide, edge cases. An edge case is an input at the boundary of valid input. The spec lists some, others you must infer. Ask 3 questions. What is the smallest input, the largest, and the weirdest? An empty file should print nothing and exit with code 0. It might break if the code assumes the array already has data. A file with one word should print 1, then the word. An off by 1 bug in the sort or the print loop could break it. A word longer than 63 characters should be truncated to 63. Without a bounds check, it could overflow the buffer. A file of only punctuation should print nothing, because the list is empty after tokenizing. And dash and 0 should print nothing, a loop that runs 0 times. Every one of these maps to a specific piece of code you will write and test. Now the analysis shifts from what to how. You have the inputs, the outputs, and the edge cases. The next question is, which C constructs do you need? Start with the data. The program stores a collection of words, and each word has a count. That pairing is exactly what a struct is for. This is struct word count. It holds a character array called word, sized 64, and an integer called count. Why 64? The spec sets a maximum word length of 63 characters, and you need 1 extra byte for the null terminator. 63 plus 1 is 64. There is a problem. You do not know in advance how many unique words a file has. A tiny file might have 10. A whole novel might have 20,000. You cannot pick a fixed size. So you need a dynamic array, an array that grows as you add words. This is struct word list. It holds a pointer called entries, which points to the array of word counts. It holds size, the current number of entries, and capacity, the number of slots you have allocated. This is exactly the realloc growth pattern from chapter 8. When size reaches capacity, the array is full, so you double the capacity and keep going. Nothing here is new. Now the reassuring part. Every step of this program uses a concept you have already learned. Step 1, parse the command line arguments, uses argc, argv, strcmp, and str to L. Step 2, open the file, uses fopen and peror. Step 3, read lines and extract words, uses fgets, pluses alpha and to lower. Step 4, search and count words, uses a linear search, strcmp, and realloc when the array is full. Step 5, sort, print, and free, uses qsort, printf, and free. Not one step needs anything new. Before you write any C, write pseudocode. Pseudocode is plain language logic. It lets you check your thinking without getting tangled in syntax. This is the whole algorithm. Parse the arguments, printing usage and exiting if the file name is missing, with top-in defaulting to 10. Open the file, calling paror and exiting on failure. Create an empty word list. Then for each line and for each word, lowercase it, truncate it to 63 characters. Search the list and either increment an existing word or add a new one with count 1. Close the file. Sort by count descending, then alphabetically. Print the smaller of top n and the list size, and free the word list. Now check each requirement against a line. Empty file. The loop runs 0 times, the list stays empty, nothing prints and you exit 0. Correct. Now a real design decision. Which data structure should hold the word list? Look at the access pattern. The critical operation is search because it runs once for every word in the file. First, a quick word on the notation. Big O describes how the work grows with the number of items. Order n means the work grows in step with the count. Order 1 means it stays about the same, no matter how many items there are. Option A is a dynamic array with linear search. It searches order n. It is simple, and you already built dynamic arrays in Chapter 8. Option B is a hash table. It searches order 1 faster for huge inputs, but it needs a hash function and collision handling, which are hard to get right. So which wins? For typical text, a few thousand unique words, linear search is fast enough and far simpler to get correct. Option A wins. Simpler code that is fast enough beats complex code that is faster. This picture shows that decision. Start at the design question on the left. It leads to a decision node, input size. If the input is fewer than 10,000 unique words, which is typical for text, the flow goes to the dynamic array with linear search, order n, simple. That is the choice for this project. If the input were more than 100,000 unique words, a hash table or sorted array with order 1 or log n search would make sense. But for a capstone, that is overkill. The picture makes the rule visible. Match the data structure to the actual input size, not to what sounds impressive. The last planning tool is a requirements checklist. It turns the specification into a verifiable list. Each row maps one requirement to the code path that implements it. Requirement 4, print usage on no arguments, maps to the argc less than 2 check. Requirement 5, paror on file not found, maps to checking the return value of fopen. Requirement 7, case-insensitive matching, maps to calling to lower during extraction. Requirement 11, break ties alphabetically, maps to a secondary SDR-CMP in the comparator. Requirement 16, zero val grind leaks, maps to freeing all your allocations. This checklist is your compass. Let's finish with 2 common mistakes. The first is coding before you understand the spec. What you do is read the specification once, then immediately start writing main. What happens is that halfway through, you discover you misread a requirement. Say you stored words in their original case, and now case-insensitive matching forces you to rework the data structure, the search, and the comparator. The fix: read the spec twice, write pseudocode, build the checklist, then code. 30 minutes of planning saves hours of rework. The second mistake is choosing a data structure before you understand the access pattern. What you do is reach for a hash table because it has order 1 lookup, so it must be the best. What happens is you spend hours on a hash function, collision resolution, and rehashing, all for a program that processes a few thousand words. A linear search would have been fast enough. The fix: analyze the access pattern first. How many elements? Which operation is frequent? Is the simpler option fast enough? Choose the simplest structure that meets the need. Let's recap. A specification tells you what the program must do. You figure out the how, and all that planning happens before you write any code. A spec defines the inputs, the outputs, the constraints, and the error cases, but not the implementation. Requirements analysis means listing every input, output, and edge case up front. You map those requirements to C, a struct for each word and a dynamic array to hold them. You choose data structures by their access pattern, picking the simplest one that is fast enough. And pseudocode and a checklist let you verify the plan against the spec before you write a line of C next. You have a specification and a plan. In the next section, you will break wordfreq into modules, design the header interfaces, and build it one module at a time.